we're going to very briefly look at friction loss models for nuclear reactor systems. Now, rod bundles are important systems for nuclear reactors. The reactor core, as well as some types of heat exchangers, can be modeled as a rod bundle. So we really need to have good friction loss models for these types of geometries. This is a little bit easier than some other systems because the rod bundles are almost always made out of a machined metal surface, and the roughness on that surface depends on the machining process rather than the material. So the surface roughness is almost always the same, regardless of what kind of rod bundle you're looking at. So what we can do is absorb the surface roughness into some empirical constant, and we don't have to model it explicitly. So that helps simplify the form of the equations. The models are very empirical. You can see the one here, developed by Chang and Chodreas. It's pretty representative of the different types of models for friction factor and rod bundle, where you have some kind of modified constant and the Reynolds number to some power. And in this case, the Reynolds number is based on the hydraulic diameter rather than, say, the rod diameter. So you have to take the flow area of the rod bundle, divide by the wetted perimeter, which is all of the edges of all of the rods and so on, to get the hydraulic diameter. And you can see the constant here depends on the pitch to diameter ratio. The pitch is the center to center distance between two rods, and the diameter, of course, is the outside diameter of the fuel rod. And the constants in this equation depend on the type of geometry, what type of subchannel you're looking at, whether the flow is laminar or turbulent, what range of pitch to diameter ratio you're looking at. So there's a lot of considerations that go into here, which is one of the reasons that the models are very, very empirical. In addition to the major losses, we also have to look at minor losses in reactor components. And the major components here are going to be entrance losses from the core bottom plate and the nozzles at the bottom of the fuel bundles, as well as exit losses in the upper part of the core where you have support structures and things in the top region. There's also going to be form losses due to the presence of spacers. Now, the spacers in a nuclear reactor perform some key functions. They prevent the rods from shaking due to flow-induced vibrations and turbulence. Reducing the vibrations in the fuel rods helps to reduce metal fatigue and prevent fuel failure. It also helps prevent the rods from deforming during operation. When the rods heat up, the material becomes less dense and it tends to expand. And when that happens, if you don't have proper support, the rods can bend. And when that happens, it changes the geometry inside your reactor, and you can end up with a reactivity insertion. So the grid spacers help to prevent those types of reactivity insertions. Now there's two major approaches to modeling the friction loss due to these types of spacers. The first is to just use the spacer Reynolds number. So you get the hydraulic diameter of the flow through the spacer, as well as the velocity of the flow through the spacer to get the Reynolds number. The other approach is to use the Reynolds number based on the bundle. So here you use the velocity through the bundle rather than the spacer, and the hydraulic diameter of the bundle rather than the spacer to get the Reynolds number. And so you have a different constant or drag coefficient. So in both cases, though, this head loss is based on the flow velocity in the spacer region. So this V sub s in these equations is the velocity through the spacer. So you need to go back and use your conservation of mass, right? Velocity times area in the bundle equals velocity times area in the spacer. And then you need to have your area ratio between the spacer and the bundle in order to complete the set of equations. Now, we can't use the velocity through the rest of the bundle as the spacer velocity because the spacer takes up some space. So the velocity in the spacer is always going to be higher than the velocity in the bundle. It's also important to note that this bundle Reynolds number version has a much more stable value for the drag coefficient. You can see that from the graphs here. So it may be a more reliable parameter than using the spacer Reynolds number directly.